Hi everyone and welcome to another digital design class. A quick announcement that I've already posted your first homework on Canvas. If you have any questions about it, please send me an email. It's mainly on number base conversion, and you have, I think, 10 days to complete and submit. The homework must be submitted in a PDF format. And when you scan your homework, or if you're doing it on your tablet, just convert it to a PDF. And if you're taking pictures, make sure that it's a high quality and you can read it. Because if you can't read it, I can definitely read it, and I can't give you the grades for it. So we covered complements, and where do we use complements? We use complements for subtraction. Today, we're going to start with signed. We also mentioned signed binary numbers and how the system works. Today, we will continue with other type of binary numbers, including BCD binary codes and ASCII and so on, and Gray, and other type of binary code systems. So another type of binary code that we use is called the BCD code. The BCD code is a 4-digit code. It starts from 0 and it goes up to 9. So it's between 0 and 9. Again, it's 4-digit. It's 0, 0, 0, 0. Start from 0, 0, 0, 0, which is 0, then 0, 0, 0, 1, which is 1, goes all the way to 9. A BCD code doesn't have 10, which is 1, 0, 1, 0. Doesn't have 11, which is 1, 0, 1, 1. Doesn't have 12, which is 1, 1, 0, 0. Doesn't have 13, which is 1, 1, 0, 1. And doesn't have 14, 1, 1, 1, 0. And doesn't have 15. So in a BCD code, we don't have 10 to 15. 10 to 15 does not exist. Only the numbers are between 0 and 9, and this is very important. So a number with k decimal digits will require 4k bits in BCD. So the decimal 396 is represented in BCD with 12 bits. Each digit is decimal digit is represented with 4 bits. So 3, we know it's equal to 0, 0, 1, 1. 9 is equal to 1, 0, 0, 1. And 6 is equal to 0, 1, 1, 0. So we write it as 3, 9, 6. Okay, 3 digits. With each group of 4 bits representing 1 decimal digit, a decimal number in BCD is the same as the equivalent binary number, only when the number is between 0 and 9. If it's greater than 9, it's 2 digits. You can't convert it directly from binary to decimal. In that case, it's a BCD code. The binary combination 1010, which is equal to 10, through 1111. So from 10 to 15 is not used and have no meaning in BCD. So only single digit decimals are used. We don't have 10, 11, 12, 13, 14, and 15. Now, these are some examples. We want to consider a decimal number 185 and its corresponding value in BCD binary. So 1 in BCD would be equal to 0, 0, 0, 1. 8 is equal to 1, 0, 0, 0. And 5 is equal to 0, 1, 0, 1. But if I want to convert 185 to binary, it's going to be shown like this. And you can see that this is a BCD code. This is in the base of 2. Okay. So if I convert this directly to this, it would be like this. 2 in the power of 0, 2 in the power of 1, 2, 2 in the power of 3, 2 in the power of 4, 2 in the power of 5, and 2 in the power of 6, which is 0, 2 in the power of 7. So it's going to be 2 in the power of 7 plus 2 in the power of 5 plus 2 in the power of 4 plus 2 in the power of 3 plus 2 in the power of 0, which gives us 185. But the BCD code is completely different. Now, to better understand this, I'll give you a few examples. I'll give you a few minutes to think on them, and then I would start solving them. So I have the following binary code. The binary code is 1 0 0 1 0 1 0 1 1. This is a binary code. I want to find the decimal base of 10 and also the BCD code for this. So I have a number 1 0 1 0 1 0 1 1. I want to find the decimal and BCD number. Do you have the answer? What is the answer? Base 10 is 299. Perfect. So let me give you this as a multiple choice and I'll explain why I'm doing this. So imagine the answers for this are 163, 299, 512, and 62. How many bits do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes? Am I correct? What is 2 in the power of 9? 512. So if I had a 1 over here and all of them would 0, so if every single bit here was 1, then I would have what? 511, yes? So there's no way that this number will reach 512, okay? Now this bit over here, this is the 8th bit. 0, 1, 2, 3, 4, 5, 6, 7, 8. Am I correct? What is 2 in the power of 8? 256. So immediately I realized that anything below 256 is also out of the picture. And most multiple choices that I give in my exam and also in FE, you can immediately eliminate them by just looking at the number. You don't need to go and calculate everything. You just count the number, the digits that you have, and then you can eliminate half of them immediately. Okay. So just with looking at it, but if you want to do it, this is 2 in the power of 0, 2 in the power of 1, 2 in the power of 2 is 0, 2 in the power of 3, 2 in the power of 4 is 0, 2 in the power of 5 is 1, 2 in the power of 6, 2 in the power of 7, and 2 in the power of 8 is also 1. So 2 in the power of 8 is equal to what? 256. So 256 plus 2 in the power of 5 is 32, 2 in the power of 3 is 8, 2 in the power of 1 is 2, and 2 in the power of 0 is 1. Okay. Now, this would be equal to 299. Okay. Now I want to convert it back to BCD. Each bit is converted to a 4-digit BCD code. So 2 is equal to 0010, 9 is equal to 1001, and 9 is equal to 1001. So it's going to be the BCD code for this is going to be equal to 0010, and with I'm going to put a little distance between them, and then after that it's going to be equal to 1001, and the last one is going to be 1001. This is the BCD code. I will solve another one. Okay. So this is the BCD code that we have. The BCD code that I have is 1001,001. And this is my BCD code. And I want to convert it to a decimal in the base of 10 and also a binary code in a base of 2. I'll give you a few minutes to think on this. We're going 7. What did you do when you had 7 digits of a binary? Yes, exactly. So what is the number going to be? Now, this is your options, okay? Without even, so the options are for decimals, they are 3, 8, 4, 6, 4, 9, 2, 4. What is it going to be? So just by looking at it, I can immediately eliminate all of these numbers. How can I eliminate them? The number ends with a 1. When the number ends with a 1, it's an odd number. So I can immediately eliminate all the even numbers, okay? So this is gonna be 4 and 9, so 49. What is the binary number for this? I'll give you a few minutes to think on it for a binary. Does anyone have the answer? Yes,
1, 1, 0, 0, 0, 1.
perfect, yes. It's 1, 1, 0, 0, 0, 1. Actually, this one is pretty easy. Just by looking at it, I could tell without doing any calculations. One way that I could show you that it could help you in your FE exam or in multiple choice exams is when you look at the number, what is the closest number, the power of 2 number to this, which is less than this? Yes, it's going to be 32. Yes. And 32 plus 17. What is the closest number to 17? So it's going to be 32 plus 16 plus 1. 32 is 2 in the power of 5. 16 is 2 in the power of 4. And 1 is 2 in the power of 0. So 2 in the power of 0 is 1. 2 in the power of 4 is 1. 2 in the power of 5 is 0. And the rest is 0. Okay. So you don't even need to do the division and the remainder and everything. Do you want me to give you another one for practice? Yeah. Okay, give me a random number, a 3-digit random number.
Three-digit?
Yeah, 3-digit random number.
101.
101. Okay. A decimal. Give me a decimal. Is 109 okay?
Yeah.
109. Okay. So 109. And I want to convert this to a binary and also a BCD code. I'll give you a few minutes to think on it. I have a quick question. Do you prefer this method of teaching, of me solving a problem, and because this takes more time? Or you just want me to go through the examples of the PowerPoint and go faster? Which one do you prefer? I can just read through the PowerPoints and they have examples without solving any problems. Do you like this method or just going through? giving you time to think on them. Okay.
I prefer having examples to solve.
Okay, perfect, yeah. And based on my experience, I've been teaching this for several years, I think 6 or 7 years. Students learn better when they do hands-on, and solve problems. So let me know when you're done with this. Okay, what is the answer? The binary?
1, 1, 0, 1, 1, 0, 1.
Perfect. So again, the other method, you need to find the closest number, the power of 2 number. Obviously, 128 is bigger than this. So the next number is going to be 64 plus 32 plus, so 64 plus 32 gives us 96 plus 13. So it's going to be 8 plus 4 plus 1. This gives us 109. 64 is 2 in the power of 6, 2 in the power of 5, 2 in the power of 3, 2 in the power of 2, and 2 in the power of 0. 2 in the power of 0, 1, 2 in the power of 2, 2 in the power of 3, 2 in the power of 5, and 2 in the power of 6. That's going to be 1, 1, 0, 1, 1, 0, 1. 2 in the power of 2 is 0. And 2 in the power of 4 is 0. And the rest is 1. So if I had 129, for example, that would be much easier because this would be 124 plus 5, which 5 is again 4 plus 1. Yes. 124 is 2 in the power of 7, 4 is 2 in the power of 2, 1 is 2 in the power of 0. So
128, right?
I'm sorry, 128. Why did I? Yeah. I'm so sorry. Yeah. 129. Yeah. Thank you for the reminder. So 128. Now my pen stopped working. Okay. So 128 plus 1. Thank you for the 2 in the power of 0. So it's going to be 2 in the power of 0, 1, 2 in the power of 1, 2, 3, 4, 5, 6, 7. And 2 in the power of 0 is 1, 2 in the power of 1, 2, 3, 4, 5, 6, 7. So it's going to be 1, 0, 0, 0, 0, 6 zeros, and 1. Now the BCD code for 109. This is 1001. This is 0000, and this is 0001. So we're gonna have 0001, 0000, and 1001. Now, one last one, and then we can go to the next part of a BCD. We have the following BCD number. It's 0110, 1100, and 0001. It's a BCD code, and we want to convert it to a binary code, the base of 2. Okay, that's a good question. Okay, the BCD numbers are between 0 and 9. What is this number? Yes, what is this number? 12. And what is this number? So this number doesn't even exist in a BCD. So this completely unrealistic. It's impossible to have this number. The numbers, digits can be only between 0 and 9. You can't have a number above 9. Now you may ask, if we don't have a number above 9, what if I add two BCD numbers like 0110 plus 1001? Both of them are by BCD numbers. This is equal to 6 and this is equal to 9. So when I add them, I get 1, 1, 1, 1. Am I correct? Which is, sorry, 6 and 9. 1, 1, 1, 1. Which is equal to what? 15. And 15 is not acceptable in a BCD number. So how do we write that? By the way, sorry for if I write my zeros small and sometimes my numbers, I actually have to translate on my mind. In my native language, we write 1, 2, 3, 4 like this. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these zeros are much smaller. That's the reason I just have to, and the question mark is actually the opposite, because we write from right to left instead of left to right. So sorry if sometimes I do the confusion. And I write my zero that's out of habit a little smaller, but these ones are also zeros. Okay. Anyway, 6 plus 9 is 15. How do I write 15 in BCD? Okay. Perfect. Yeah, actually, yes, you have to convert this to two numbers. So I have to write it as 0, 0, 0, 1, which is 1. And what was the other one? Perfect. 0, 1, 0, 1, which is 5. Now, how can I go from this number to this number? The computer, how does it know to do that? It has a 4-digit number. How does it know to go from this to that? So the binary numbers are from 0 to 9, okay? Is it correct? And if I have a carry on, it means I skip 10, 11, 12, 13, 14, 15, and then I go back to 1. Am I correct? What is the difference between 9 and 15 back to 1? 6. So what I do is whenever I have this problem, I would simply add 0, 1, 1, 0 or 6 to it. So if I have 0, 1, let's add 0, 1, 1, 0 to it. It's going to be 1. 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 1, 1. 1 plus 1 is 0, 1. And then I add the zeros at the end. So now I have 0, 1, 0 and 0, 0, 1. 0, 0, 0, 1, which is 1, 5. So I add 0, 1, 1, 0, which is equal to 6 to it. So I would start the table all over again. Does it make sense? Okay. Now these are some examples. For example, if I want to add two BCD numbers, 4 plus 5, this one is easy. Let me go on slideshow. easier with the slideshow. Um, it's not. Can you see it here? Is it clear? So 4 plus 5, if I do it with the binary, with the BCD code, 4 is equal to 0, 1, 0, 0. And 5 is 0, 1, 0, 1. And when I add them, I get to 1, 0, 0, 1. And this is still in a BCD range. Not going off. So I'm not gonna have any problems here. But what if I add 4 plus 8? If I add 4 plus 8, 4 is 0, 1, 0, 0, and 8 is 1, 0, 0, 0. And then I get 1, 1, 0, 0, which this number here now is not in the BCD range. It's in binary, it's 12, but in BCD, it doesn't make any sense. So what I do, I add 0, 1, 1, 0, or 6 to it, and then I get 1, 0, 0, 1, 0, which then I could add these 3 zeros over here. This is going to be 2, and this is going to be 1. So I have 1, 2 in binary, in BCD. Same thing here as well. So 9 plus 8. So 1, 0, 0, 0 plus 1, 0, 0, 1. The result would be 1, 0, 0, 0, 1. Again, this is out of our range of a BCD. It's a 5-digit actually. So what I do, again, I add 0, 1, 1, 0 to it, and I get 1, 0, 1, 1, 1. And this is equal to 7. And this, when you add the zeros, is going to be 1. So I'm going to have 17.
Always just add 6.
You always add 6. If it's out of the range of it's above 9, you add 6 to it. Yes. Now let's solve a practice problem. I want you to add 1, 0, 0, 1 in a BCD to 1, 0, 0, 1. So 1, 0, 0, 1 to 1, 0, 0, 1. So what is the answer? So 1010 is equal to 9, 1010 is equal to 9. If I add 1 plus 1, it's going to give me 0, 1. This is going to be 1, 0, and 1 plus 1 gives us 0, 1. Obviously, this is out of the range. It's 16 plus 2, so out of range. So what I would do, I would add 0, 0, 0, 1, 1, 0, or 6 to it. So 0 plus 0 is 0. 1 plus 1 gives us 1, 0, and 1 plus 1 gives us 1. Zero plus 0 is 0. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. And this one comes here, and I add 3 zeros. This is 1, 8. So I'm gonna have 8. Did you get the same result? Okay. So this was for a single digit, decimal or 4-digit BCD. What if we have 3 digits or so? This is an example of adding a 3-digit decimal and adding it in a BCD code. So we will consider the addition of 184 plus 576 and BCD. So 184 is translated to 0001, which is 1. And 1000, which is 8, and 100100, which is 4. And 567, it's 0101. 7 is 0111. And 6 is 0110. Now, if I add 4 plus 6, I get 10, which is not in the BCD, not a BCD code. So I have to add 6 to it. Then I get 000 with 1 carry. And then I add carry to the next one. The carry is carried to the next number. Then I have 1000 plus 0111 plus the one that we had from carry. And if I add these two again, I get a number that is out of the BCD code. I add 6 to it. Again, I have another carry. I add it. And the last one, it's actually in the BCD range, so I would keep it without adding 6 to it. Now the final BCD sum would be 0111, which is 7, 0110, which is 6, and 0000, which is 760. And we can do decimal arithmetic as well. For example, it's 375 plus negative 240. And for that, what I can do is instead of negative 240, I can write the complement of negative 240, which here the complement of negative 240 is going to be 760. And when I add them together, I get 135. So we're using tens complement of a BCD to do that. Now, let me solve another problem. Give you another example. Let me give you another example. We want to add 5, 7, 9 plus 8, 4. Oh no, let's make it 2, 4, 3. And I want to do it in BCD. We want to do this addition in BCD. I want you to convert it to BCD, do the addition in BCD, and convert it back to decimal. 0, 1, 1, 0. 0, 1, 1, 1. Because you added the carry on from the previous one. Oh, yes. Yeah, that's gonna be 7. So it's gonna be 0, 1, 1, 1. Need more time, or do you want me to solve it? Okay, so can you help me with 5, 7, 9? What is that in BCDs? 5, 7, 9. It's gonna be 0, 1, 0, 1, which is 5, and then 0, 1, 1, 1, which is 7, and 9 is 1, 0, 0, 1. Okay, so this is 579. And 2, 4, 3 is gonna be 0, 0, 1, 0. 4 is gonna be 0, 1, 0, 0, and 3 is gonna be 0, 0, 1, 1. Am I correct? Yes. It's going to be 2, 4, 3. Now let's add them together. 1, 0, 0, 1 plus 0, 0, 1, 1. What is this equal to? So 1 plus 1 is 0. And then 1 plus 1 is 0. And then 1. And then 1. Okay. So it's going to be 1, 1, 0, 0. 1, 1, 0, 0 is equal to what? 12. 12 is out of the range. So I would add 6 to it. Or 0, 1, 1, 0 to it. So 0 plus 0, 1 plus 0 is 1, 1 plus 1 is 0, 1, and 1 plus 1 is 0. And I have 1 over here that it will be added as a carry on to the next digit. So the first 4 digits is going to be 0, 0, 1, 0. Now 1 plus 1 plus 0 gives us what? 0, 1, 1 plus 1 gives us 0, 1, 1 plus 1 plus 1 gives us 1, 1, and 1 comes over down here. Now, what do you have here? I have 1, 1, 0, 0, which again is equal to what? 12. Then I have to add 0, 0, 0, 1, 1, 0 to it. Again, I would have 0, 1, 0, 0, and a 1 that it's been carried on over here. Now, the last digit is going to be 1 plus 1 is equal to 0. 1, 1 plus 1 is equal to 0, 1. 1 plus 1 is equal to 0 and 1. Gonna be here. So first digit is gonna be 8. This one is gonna be 2. This one is gonna be 2. So the result would be 8, 2, 2. Am I correct? Did you get the same answer? So 9 plus 3 is gonna be 12. 8 plus 4 is gonna be 12. 6 plus 2 is gonna be 8. If you solve it, gonna get the same answer, 8, 2, 2. 822. Is it clear, or do you want me to solve another one? Clear? Can I move on to the next? Okay. So this shows different types. So we have a bunch of different types of binary and decimal codes as well. We have the BCD 8421, the 2421, the excess of 3, 4, 8, -2, and so on. And it's just not BCD. We have other types, but the most popular one is BCD. Another type of binary code that we have is called the gray code. The advantage of the gray code is, again, the gray code doesn't follow the normal, binary to decimal changes that we had. The gray code is designed in a way that when going from one digit to the next digit, only one bit is changing. So it's specifically designed in a way that when you go from one digit to another, so for example, if you want to go from 7 to 8 in a binary to decimal, you have to change 4 bits. Okay, if you go from 7 to 8, so 7 is 0, 1, 1, 1, 1, 8 is 1, 0, 0, 0. So you have to change all 4 bits just to add one number. Okay, but in a gray code, it's not. And we follow another path direction. So for a gray code, we start from 0, 0, 0. Then we change 1 bit. So 0, 0, 1. This is up to this point is similar to binary to decimal, but from now on it's different. And then 2 is 0, 1, 1. So I just change another bit. 3 is going to be 0, 1, 0. 4 is going to be 1, 1, 0. 5 is going to be 1, 1, 1. 6 is going to be 1, 0, 1. And 7 is going to be 1, 0, 0. If we have a 4-bit, it's going to be 1, 1, 0, 0, then 1, 1, 0, 1, and then 1, 1, 1, 1 is 10. But in binary, that's 15 actually. So 11 is going to be 1, 1, 1, 1, 0. 12 is going to be 1, 0, 1, 0. 13 is going to be 1, 0, 1, 1. 14 is going to be 1, 0, 0, 1. And 15 is going to be 1, 0, 0, 0. Why do we use a gray code? First of all, it's for error detection. Okay, if you're using a counter and suddenly you see 3 bits changing instead of 1, you know that there has been an error. It's good for representation of analog data because you want to move smoothly, and you want to have a continuous data. And the most important advantage is low power design. So we know that each of these binary digits represents a level of voltage. So when you go from 0, 1, 1, 1, you're going from 0 volts, 5 volts, 5 volts, 5 volts to 5, 0, 0, 0. So you have a huge change in the voltage. But if I go, for example, from 0, 1, 1, 0, 0, 1, 0, 0, 1 to 1, 0, 1, 1, I'm just changing 1 bit voltage. So I'm not changing all the 4-bit voltages. So I'm going to consume 1/4 of the energy if I'm going the other one. So another reason is because of the lower power design. At each stage, you're only changing the voltage of 1 bit. You're not changing the whole byte voltage or the 4 of the 5-bit voltages or something like that. Another type of binary code is called the ASCII, or they call it ASCII code. In one of the your homeworks, I already mentioned this, but you already know how to do a binary. So ASCII code is a binary code that is actually some symbols that we show as a binary code. And it's the American Standard Code for Information Interchange. And this technically came when computers came out and they wanted to type on a keyboard. Each key on the keyboard represents a letter or a sign, like for example, question mark or exclamation mark or a dot or a space A, B, or anything. And the computer only understands in ones and zeros. So what we have to do, we have to convert like A or B or C to a 4-bit code, for example. And then that was when the ASCII code was developed. And for example, if we wanted to show A, we would show it with 8 bits. The four higher bits are, for example, for A are 0, 0, 1, and the lower ones are 1, 0, 0, for example. And then we get 8 A or different numbers. So how many characters can I show with an ASCII code that has 8 bits, for example? 2 to the power of 8 is equal to what? Is equal to 250. So I can show up to 256 characters. So for example, if all of them are 0, it's equal to null, for example, or it's equal to B. And if all of them are 1, it's equal to delete, or I don't know, J, you know? And then, and this shows the rest of it. This is the ASCII character control as well, and a code as well, that we can show backspace. We can show, for example, shift in, shift out, space, and so on. When they initially designed this, they didn't think of, I would say, other languages. And the initial ASCII codes were only able to show 256, for example, characters. So if Microsoft wanted to come up with a word that had, I don't know, Mandarin or Arabic characteristics, or Latin characteristics, or even mathematical, equations and symbols, they couldn't do it because they ran out of, digits and symbols to do that. So what they did, they actually added to the numbers. So instead of having 8-bit, they went to 9, 10, and so on. So when you have 10 bits, you can go up to 1024 characters. Therefore, you could show different Persian, I don't know, Arabic, Chinese, Korean, all these Japanese, all these different characters from different languages as well. So you could show different, symbols, mathematical symbols, and so on. So American Standard Code from information interchange is referred in the previous table. Popular code used to represent information sent as character-based data. It's, as I mentioned, usually it was initially designed to transfer data from the keyboard to the microcontroller. The initial one uses 7 bits to represent 94 graphic printing characters and 34 non-printing characters. But again, it was expanded later on. Some non-printing characters are used for text format, e.g. BS is equal to backspace and CR is carriage return. Other non-printing characters are used for record marking and flow control, like SCX, ETX, and so on. ASCII has some interesting properties. Digits 0 to 9 span hexadecimal values 30 the base of 16 to 39 in the base of 16. And uppercase AZ span from 41 in the base of 16 to 58 in the base of 6. And lowercase AZ spans from 61 hexadecimal to 78 hexadecimal. And the lower to uppercase translation and vice versa occurs by flipping bit number 6. So again, other problems, initially you could just do like uppercase, then we added to it, and now it cover a whole bunch of characters and so on. Now, another type of binary code that we use is for error detection code. And this is a very clever, genius way that you can actually find the code, and we have other methods that you can determine which code actually is wrong. And especially when you're doing long distance transmission, that's critical to see which bit has error in it. So what we do, a simple one, is we add a bit called a parity bit. And the way that we do is we would add a bit and make that digit either even or odd, the number of ones. So for example, with an even parity, how many ones do I have? I have 2 ones. For odd parity, I would have 3 ones, okay? So if I send this and I tell the receiver that I have sent an odd parity and they see 4 ones, for example, instead of 3, and this is an odd, an even number of ones, I have 4 ones, then the receiver would realize that this code is incorrect and it would discard. Okay, so I would send a single bit, and I can tell this is my parity bit. If this bit is 1, it means the code is even parity. If it's 0, it means it's odd parity. Okay, so imagine I send this digit and I send a 1 after it, meaning this is the even parity, and then the computer, the receiver would check it and see, oh, it has odd numbers of ones, and immediately it will realize that there has been an error. Okay, is it clear? Yes. Okay, so A parity bit is an extra bit included with the message to make the total number of ones either even or odd. And when we have communications between two devices, initially we would determine that all the data that I'm going to send you would have even parity. Okay, so it means everything that I would send you would have even numbers of ones. So if the receiver receives something that has odd numbers of ones, it immediately understands that this is an error and it's going to discard it. And usually they would ask the transmitter to send the data again. Okay. So another type is called the redundancy, or what we call the error detecting code or redundancy. We provide extra information in the form of extra bits and can be incorporated into binary code words to detect and correct errors. A simple form of redundancy is parity, an extra bit appended onto the code word to make the number of ones odd or even. Parity can detect all single bit errors and some multiple bit errors. A code word has even parity if the number of ones in the code word is even, and a code word has odd parity if the number of ones in the code word is odd. This is an example of message A and B. Message A is even parity, and message B is odd parity. This causes a little problem as well. The problem that we have if we send this redundancy code is we are limiting our bandwidth. Some part of the bandwidth is occupied for these redundancy codes, so it doesn't have any useful information, and it just adds to the amount of data. So imagine if you're sending a video, 400 megabyte or something, and every 8 byte you have one extra bit, then you have like 40 megabytes, something like that, of redundancy bit that it's useless. And 40, meg is a large number. And we have other means and other ways to actually compress the data and transmit it and find the error as well. Now, let's talk about, I think it's enough for today because I don't think we have enough time to finish registers. Yeah, I think it's, let's finish the registers because, and then for the logic gates, we would do it on Thursday. So why do we need a binary system, and how does the binary system works? In a computer, usually we have memories and what we call binary cells, which are single bit memories. And they are usually made out of a transistor and a capacitor, or a transistor or even a capacitor that holds one bit of information, a 0 volt or a 5 volt, something like that. So, and the one binary cell are usually called registers. The registers are a binary cell, a bunch of binary cells. And a binary cell is a device that possesses two stable states and is capable of storing one or two states. So it could store, for example, 0 volts and 5 volts. Imagine you have a battery, and that battery is either full, 5 volts, or it's empty. Okay, so a battery is a long-term memory. A lot of memories that we have are short-term memories, like the memories in your computer, like a RAM. They would only hold the memory, the value, as long as they are powered. As soon as you cut the power or reset it, it's going to be erased. Okay, so that's called a random access memory. Some memories are permanent, like a CD drive, DVD, or a flash drive. Flash is not like, permanent, but it holds data for a long time. If you even cut the power from those, it's going to retain the memory, or a hard drive. And a register is a group of binary cells. A register with n cells can store any discrete quantity of information that contains n bits. So if you have n cells, you're going to have 2 in the power of n possible states. For example, if you have 3 cells, you're going to have how many states? 2 in the power of 3 is equal to what? 8, between 0 and 7. Registers are the faster, usually the fastest type of memories, and they are the fundamental building blocks of a computer. So a binary cell is a two stable state. It stores one bit of information. Examples are flip-flop circuits, ferrite cores, and capacitors, batteries. A register is a group of binary cells. For example, when you have AX and x86 CPU, the registers that we have memories. A register transfer is a transfer of the information stored in one register to another, one of the major operations in digital system. And this is an example in this slide. This is a digital computer example. We are connecting a memory to input output. So for example, you're playing a music or a music video from your memory, and the output could be your speaker and your screen. So first you give the coordination of the memory and say, okay, pick this from drive E, for example, brings it to the CPU, does some processing on it, and it sends it, if you want to show that, go through the GPU and it finally shows on your monitor. The inputs could be anything from keyboard, mouse, and microphone, and so on, camera even. Outputs could be your monitor, modem, printer, all of those could be. So give it an input, a coordination, process it, summons the data from the memory and gives it as an output. This is an example of transfer of information. You can see that the keyboard, when you put John, for example, JOHN, it will convert it to, for example, an ASCII code. ASCII code that is an 8-bit code. It goes to the process unit. It finds that you can see John, JOHN on the top, which has a specific place in the memory, and it would get that from memory and it could show it on your printer, for example, or your screen. The other major component of a digital system is the circuit elements to manipulate individual bits of information, like a load store machine, like load R1, load R2, or add R1, R2, and R3 and store the data R3, so for example. So you can load two data, two numbers, add them, and then store the result as well. But you can manipulate numbers, graphics, voice, and then store it again. I think it's enough to this point for this week, for this class. And in the next class, I will start with digital logic gates. And when we are done with digital logic gates, we will start with our labs. So we're going to have labs after we are finished with digital logic gates. Thank you so much, and I will see you on Thursday.